Good day, everyone. It's a pleasure for me to be here today and present a brief overview about stone deterioration and conservation. First of all, why are we interested in conservation of stone and more in general of cultural heritage? I think the first reason is that cultural heritage substantially contributes to define our identity as a society. Moreover, it's also an important source of wealth through tourism and economic activities linked to cultural heritage management and conservation. For these reasons, the United Nations have included the safeguard of cultural heritage among the Sustainable Development Goals. So to start with, stones are usually classified based on their origin as igneous, sedimentary, or metamorphic rocks. Depending on their origin, the final chemical mineralogical properties of stones, as well as their physical mechanical properties, may change also significantly. In terms of building stones, the use of the different lithotypes around the globe depended, of course, in the first stage on the local availability of different stones, as well as their physical mechanical properties. If we try to generalize, I think we can state that the most used lithotypes were sandstones, limestones, and marbles. So sandstones are usually composed of quartzitic grains that are held together by a cement that can be calcareous in nature or can also contain clays. The porosity of sandstone may be low, but it could also reach very high values. Limestones are sedimentary rocks as well. In terms of composition, they are virtually composed of 100% calcium carbonate, which constitutes both the grains and the cement. Of course, impurities of various types can be also present. In terms of porosity, limestones can have low but also very high porosity, reaching up to 40% and more. Marbles are metamorphic rocks that can be thought as originated by limestone that has undergone high pressure, high temperature. So in the end, marbles are composed of calcite grains, bigger in size compared to limestone, with no cement among each other. The porosity of marbles in the fresh state is low. We will see that all these properties determine the deterioration processes that can affect the different lithotypes. So the first part of the presentation will be about deterioration of stone, while the second part will focus on conservation strategies. So stone deterioration processes can be chemical, chemophysical, physical, or biological in nature. Some of them are common to other building materials, such as cement and concrete, while others are characteristic of stones. So one of the most widespread deterioration processes is the crystallization of salts and ice inside the pores of the material, in a similar way as it happens also on cementitious materials and concrete. So the harmfulness of these processes depends on the one hand on the supersaturation of the saline solution or undercooling in the case of ice, and on the other hand on the properties of the stone, particularly the stone pore size distribution, because we know that the smaller the pore, the higher the crystallization pressure, but also on other properties such as its permeability, and of course also mechanical properties, because damage occurs and propagates when the stone tensile strength is exceeded. A deterioration process that is typical of stones with low porosity, such as granites and especially marble, is thermal weathering. In the case of marble, for instance, thermal weathering occurs because of the atypical thermal behavior of calcite grains when they are subject to a temperature variation. In fact, they elongate along the z-axis and contract along the other two axes. As a result, this anisotropic thermal deformation leads to the opening of microcracks, because the calcite grains in marble are very tightly packed with no voids between the grains. So as soon as the grains start to deform and all of them have different crystallographic orientations, then stress arises and microcracks are formed. When this type of deterioration, of thermal deterioration process occurs in thin slabs, like in the case of tombstones or commemorative stones, then we may have a gradient in temperature and hence in damage through the thickness of the slab, because one face of the slab is exposed to the atmosphere, solar radiation, possibly humidity, and so on, while the other side is protected. And so this gradient in weathering results in bowing of the slabs, which may also lead to cracking and final collapse of the slab. Again, especially in the case of marble, another major deterioration process is dissolution in rain, especially if rain is acidic, and this is a consequence of the slight water solubility of calcite. So again, depending on the environment, on the pH of rain, this process can lead to surface loss up to 1 mm%. Even though the air quality has improved in recent years in many, at least European countries, still predictions for the future linked to climate change foresee an increase in dissolution of carbonate stones as a result of the predicted increase in CO2 concentrations and predicted increase in rain events instead of snow events following the predicted increase in temperatures. A deterioration process that, on the contrary, is typical of sandstones is the damage caused by swelling clays. In fact, we mentioned that clays can be present in sandstone in the cementing fraction. Some clays, not all of them, but some clays swell significantly upon water absorption, for instance, in the case of rain or rising dam. Some of these clays, for instance, belong to the Montmorillonite group. So in this type of clays, we have cations between the silica and octahedral layers. These cations are needed to ensure the electric neutrality of the material. Well, in case of rain, for instance, water molecules can be absorbed into this interlayer, causing considerable swelling. You can see here the swelling can reach up to 1 mm/meter, which on the macroscopic scale causes cracking and detachment of flakes that can be centimetric in size. Another type of deterioration process that affects virtually all types of stones, but especially marble and stones with low porosity, is staining caused by metallic elements that can be present adjacent to the stones. For instance, here on the left, in the case of bronze sculptures that are present on top of marble pedestals, rain causes leaching of copper ions that then are transported onto the stone surface, where they can react with carbonate ions deriving from the stone itself, thus leading, for instance, to malachite, which is a basic copper carbonate with a typical green color, and which is also very has a very low solubility, so it's also very hard to remove. On the right, you can see another example where staining instead is caused by iron elements. Another cause of stone deterioration, especially both in terms of aesthetic appearance and chemical composition, is soiling and sulfation. Soiling is basically the deposition of particulate matter, dirt, black carbon over the stone surface. This particulate matter can also be incorporated into a surface crust thus leading to the so-called black crust, because of the color, of course, in case a surface layer of gypsum is formed over carbonatic stones as a result of a chemical reaction between the stone itself and sulfur oxides that are present, or especially in Europe, were present in the atmosphere in past years. So this chemical reaction between the carbonate substrate and sulfur oxides mediated by water leads to the formation of gypsum that can incorporate these particulate matter. So when we go and restore a monument today, we need to take this into account. Finally, a type of deterioration that again can affect virtually all types of stone is biodeterioration caused by microorganisms such as bacteria, fungi, lichens, and so on. This causes several types of damage in terms of aesthetic alteration of the stone, as well as chemical corrosion because of acids secreted by the organisms, but also mechanical stress caused by penetration of these organisms in depth. On the right, you can see some examples of monuments where that are covered by gray patinas, which is constituted by the microorganisms, while the whiter parts are parts where these microorganisms do not develop, where they are killed by metal ions that are released by bronze or lead elements that are adjacent to stone. Okay, after this quick overview on stone deterioration, we will now see what are the main strategies for its conservation. So conservation interventions are usually composed of the three main phases of cleaning, consolidation, and protection. Cleaning is aimed at removing the surface deposits, dirt, black crust, and so on, and it can be preceded by another phase which is called pre-consolidation, aimed at improving the mechanical properties of the stone, in those cases when the stone is so badly deteriorated that it's not even able to stand the cleaning operations. After cleaning, we usually have consolidation, which is the application of products that are aimed at improving the mechanical properties of the stone, as we will see more in detail in the following. Consolidation can be preceded by other phases such as desulfation, so the retransformation of gypsum formed by sulfation into a more stable compound, or for instance in the case of sandstones containing swelling clays, we may have the application of swelling inhibitors, basically surfactants that reduce the swelling of the clays. After consolidation, we usually have the protection of the stone, which is the application of a surface layer aimed at acting as a barrier between the stone and the aggressive environment. Protection may be preceded or combined also with other interventions aimed at providing the stone with self-cleaning ability or with an antimicrobial action. So, as I mentioned, we will now focus on consolidants. So consolidants are liquid products that are aimed at penetrating in depth into the substrate. They are usually applied by brushing, spraying, or poulticing, and so they need to have a viscosity that is low enough to allow them to reach the unweathered part of the stone, which may be at some centimeters depth from the surface. And then after hardening, these products should bond the grains of the stone, acting as bridges, thus improving the cohesion of the stone and also its mechanical properties, with the final goal of improving the durability of the stone to the deterioration processes that we have seen. It's important to distinguish between consolidants and protectives. Protectives are again liquid products that are applied by the same techniques and that in principle also chemically can be very similar to consolidants, but in this case the goal is to form a surface layer to protect the stone and not penetrate it in depth as in the case of consolidants. In doing their task, consolidants need to meet along a series of requirements, as you can see here. So first of all, they need to be effective. So again, able to penetrate in depth and able to ideally chemically bond to the grains to improve the cohesion of the stone and its mechanical properties. In doing so, the consolidants also need to be compatible with the substrate, meaning they shouldn't alter the aesthetic appearance of the stone. They shouldn't give rise to the formation of dangerous byproducts. And of course, we are introducing a new material inside the pores of the stone, but still we would like the alterations in the porosity and precise distribution of the stone to be as limited as possible. And in a similar way, also changes in the water transport properties and exchange of water vapor between the stone and the environment should be as limited as possible. In a similar way, also the thermal properties of the treated part of the stone should be compatible, meaning similar to those of the untreated part of the stone, because any mismatch may result in the so-called delayed incompatibility, meaning in the medium-long term there could be issues of, again, compatibility leading to a failure of the durability of the treatment. So in addition to being effective and compatible, consolidation treatments also need to be durable, so the consolidant itself should be stable, not dissolve, for instance, in water or rise in damp, and again, it shouldn't give rise to delayed incompatibility. Finally, consolidants should ideally be reversible, meaning they should be it should be possible to remove them in the future, but this is basically impossible, especially for inorganic consolidants. That's why in most cases people settle for retreatability, meaning it should be possible in the future to treat the stone with either the same or another consolidant without the pores being totally filled and without the surface wettability of the stone to be altered too much. Because simultaneously fulfilling all these requirements, it's quite challenging. Research on stone consolidants is still ongoing. As you can see in this slide, research is still ongoing, especially on carbonate substrate, highlighted in yellow here in this part of the slide, while studies on silicate stones are more limited. Why? Because in the case of silicate substrates, such as sandstones, there exists a class of consolidants that we will see next, which is quite, I mean, it's really effective, so it has a good performance. So the focus of research on stone consolidants is mostly on carbonate stones like marble and limestone, because in those cases, fewer options, suitable options are available. So in the next, we will see more in detail the 5 consolidants that you see listed here, which are those that have been studied the most in recent years. So the first class of consolidants that we will see is that of alkoxysilanes. They have been in use since more than 1.5 centuries now for stone consolidation. So basically they are solutions of ethyl silicate, which is also known as tetraethyl orthosilicate, TIOS. So the idea is you impregnate your stone with a solution of ethyl silicate. Over time, there's a reaction with water molecules in the atmosphere, leading to hydrolysis of the consolidants, which finally condense to form a silica gel that can be chemically bonded to silicate substrates, such as stones, which is why I mentioned that in the case of silicate consolidants, silicate stones, we have suitable consolidants that perform quite well. You can see here on the right the binding ability of ethyl silicate, which is able to reaggregate quartzitic powder, while this is not the case in the case of calcitic powder, because in this case there are no OH groups on the surface of the mineral of calcite, that can chemically bond to the consolidants. So in the end, the effectiveness on calcitic substrate is much lower than that on silicate ones. Nonetheless, among the good points, so the strengths of ethyl silicate, we have its very low viscosity, so it's able to penetrate in depth into the consolidant, and again, it can effectively bond the silicate grains, and it has a good stability over time. However, as I mentioned, in the case of carbonate stones, such as limestone and marble, alkoxysilanes are not as effective, which is why people have proposed the use of coupling agents that are compounds that are applied before ethyl silicate with the aim of chemically bonding to the calcitic substrate on the one hand, and then after application of alkoxysilanes, these coupling agents should also chemically bond to the silica gel, and this has been shown to give increases in strength up to 100% compared to the direct application of the ethyl silicate. Other known limitations of alkoxysilanes are their tendency to crack during drying, which again reduces their efficacy. To overcome this limitation, different strategies have been proposed, such as the addition of siloxanes to make the silica gel less brittle, or on the other hand, the addition of nanoparticles to increase the elastic modulus of the gel. Another known limitation or delicate aspect of alkoxysilane is that they make the treated stone hydrophobic for a very long time, more than 6 months in the field, and this can be an issue in case water or saline solutions are present behind the hydrophobic layer, because this could lead to the detachment of the treated layer and so the failure of the intervention. To overcome this problem, strategies have been proposed, such as the application of poultices of water or water ethanol solutions to accelerate the hydrolysis of the consolidants so that the hydrophobicity can be lost in a matter of days instead of months. Again, to prevent the hydrophobicity issues shown by ethyl silicate, in recent years, another class of consolidants has been proposed, which is that of nano-silica. So nano-silica is basically a dispersion of silica nanoparticles in water, and so these silica nanoparticles have OH groups on their surface, which can then condense in a similar way as ethyl silicate. So the advantage is that basically the hydrolysis phase has already taken place. So this consolidant causes no hydrophobicity, and curing can occur in a matter of a few days instead of months. But however, because now you are applying a nanodispersion and not a solution, there could be issues of low penetration into the substrate and formation of a surface crust, which alters the appearance, the color of the stone. As we have seen previously, organic polymers have been used since the 50s. At the beginning, they showed a lot of potential because they have good adhesive properties, but still they have also shown some limitations. So the idea here is that you dissolve the polymer, the acrylic resin, in a suitable solvent, which is often acetone. You obtain a solution which typically has a 5% concentration, and then you apply it by spraying or brushing onto your substrate. As the solvent evaporates, the polymer solidifies and it's able to bond the grains in the stone. In addition to its high effectiveness, a strong point of acrylic resin is that, let's say thermoplastic polymers in general, is that they are in principle reversible. So by applying a suitable solvent, it should be possible to dissolve the polymer and so to remove it from the stone. However, experience has shown that this is mostly theoretical, because if you go on a treated stone and you try to remove a polymer that was applied some decades ago, This has undergone some reticulation over time, so it becomes impossible to remove the polymer without damaging the stone. Moreover, organic polymers have shown a lot of compatibility issues, leading to failure in their durability because they create an hydrophobic impermeable layer over the treated stone. And then again, in case there's a source of water, saline solution behind the treated stone, the water or saline solution cannot exit the stone, and so there's accumulation of salts, and this can lead to the final detachment of the consolidated layer, and again to failure. Because of the limitations exhibited by organic polymers in recent years, the research has mostly focused on new inorganic ones. In the year 2000, the use of alcoholic dispersions of calcium hydroxide nanoparticles was proposed. So here the idea is that you apply the nanodispersion onto your substrate, and then the nanoparticles react with atmospheric CO2 with time, thus finally forming calcium carbonate. Thanks to the high concentration that can be reached using alcohol for the dispersion, in this way it's possible to obtain a higher effectiveness compared to the use of the traditional lime milk or lime water. Studies have shown that nanolimes are able to significantly improve several types of substrates. However, a known limitation is that the nanoparticles tend to be retransported towards the treated surface during drying. So there's a risk of accumulation of the consolidants near the treated surface. To prevent these problems, several strategies have been proposed, such as the use of more suitable solvents and the application of a water poultice after applying the nanolimes, again with the aim of preventing the nanoparticles retransportation towards the surface. Some 15 years ago, a new class of consolidants was introduced, which is that of phosphate consolidants. So here the idea is to prepare an aqueous solution of a phosphate salt, typically diammonium hydrogen phosphate, DIP. So the solution is then applied onto the substrate by standard techniques, and then in a matter of a few hours, a chemical reaction takes place between the substrate, providing calcium ions, and the consolidant, providing phosphate ions, so that calcium phosphates are formed. Among calcium phosphate, the ideal one to form is hydroxyapatite. You can see the formula here. So hydroxyapatite, usually abbreviated as HAP, is the ideal one to form because it's the most stable calcium phosphate at pH higher than 4. And for the record, a biological apatite present in several ionic substitutions is the main mineral constituent of our teeth and bones, which demonstrates the high durability of this mineral. Several experimental studies have shown that by the application of DAP solution, it's possible to achieve very significant increases in mechanical properties of different substrates, marbles, limestones, but also lime mortars, and so on. And this is possible without causing significant alterations in the aesthetic appearance of the substrate, as well as in its physical properties. A delicate point is that DAP solutions cause some slight alterations in the pore size distribution, again, because we are introducing a new mineral inside the pores. So as you can see here, there's a tendency to partly occlude the bigger pores, thus forming smaller pores. This in principle could be an issue because we know that in case of salt crystallization and ice formation, the smaller the crystal, the higher the crystallization pressure, but still it's also true that smaller pores are harder to be filled by water and saline solutions. So Extensive testing, also in comparison with alternative consolidants, have shown that durability issues of DAP-treated stones seem not to be a major concern, at least in laboratory conditions. Indeed, here, for instance, you can see that the durability of DAP-treated limestone to freezing stone cycles was much higher, was much better than that of the untreated reference, but also in comparison with paralloid B72, which is one of the most widely used acrylic resins. So DAP-treated limestone was able to stand 70 freezing thawing cycles without a major problem. Similarly, also in the case of salt crystallization, DAP-treated samples were able to withstand deterioration cycles better than ethyl silicate treated samples. Why? Because ethyl silicate causes temporary hydrophobicity, which, as I mentioned, can lead to damage, while this didn't take place in the case of DAP. Compared to ethyl silicate, DAP solutions also have the advantage of being effective after just 24 hours instead of several months, like in the case of ethyl silicate. Similarly, also compared to nanolines, the DAP treatment has the advantage of being effective in a much shorter time, in a matter of hours instead of weeks. And in addition, the mechanical strengthening is much higher. In addition to the requirements that we have seen until now, a further important aspect that is receiving increasing attention in recent years is the environmental sustainability of stone consolidants. We have recently performed a life cycle assessment of the different consolidants that we have seen. And as you can see here, so in terms of global warming potential that is linked to the saturation of a given substrate by different consolidants, we can state that DAP leads to a lower global warming potential compared to the other consolidants, mostly because its solvent is water, while organic solvents or various compositions are used in the case of the other consolidants. Moreover, as you can see here on the right, where the mechanical effectiveness of the consolidant is plotted against the global warming indicator, we can see that DAP is able to provide significant increases in mechanical properties while causing a much lower global warming indicator compared to the alternatives. In this specific case, ethyl silicate was the only alternative consolidant that was able to reach the same level of mechanical effectiveness. But in the case of ethyl silicate, the global warming potential was basically twice as much compared to DAP. Finally, I would like to point out some open challenges that we as researchers in the field of stone consolidants and conservation products in general must face. First of all, we need to perform our studies in representative conditions, meaning the substrates that we use should be representative in terms of level of damage, presence of contaminants, presence of moisture in the pores, and so on, because these are the real conditions in the field. So to use simplified systems is suitable in the first stage of research, but then we need to move towards more realistic conditions. Similarly, also the application methods and environmental conditions that we adopt should be as close as possible to the real ones in the field. Field testing is actually another very important point, meaning we need to validate our results in the field, which also implies that we need to develop improved non-destructive test methods, because the possibilities at the moment are quite limited. In addition to characterize the performance of our products right now, we need to also assess their behavior in the medium-long term, again, to make sure that no incompatibility issues arise when the products are used in the field. For all these topics and also all the things that we have seen up to now, we also need to find improved ways of communicating our results, so solutions that have been developed by researchers to the end users of these products, meaning restorers and people that are in charge of cultural heritage conservation, because in many cases solutions are already available, but we researchers failed in transferring this information to the end users. In a similar way, we also need to find improved ways of reaching decision makers. Okay, I would like to thank all the people that make these works possible all through the years, so including my former supervisor, my former colleagues, and my current colleagues at the University of Bologna, and all the members of my group, as well as the previous and current visitors. And I would also like to thank you all for your attention and your patience. Thank you.